Hello everyone, and welcome to the Network Automation Tools and Technology Talk. For the next half hour, we're going on a fast-paced exploration of what network automation means today. What are the key concepts and problems this technology is solving? Starting with the network automation landscape, which is my current interpretation and overview of the technology areas, we will briefly dive into what challenges are addressed and what tools are available in each of the four main topics. About myself, I am a consultant and trainer, originally from Romania, now living in Ireland. I've grown with programming and Linux and games, but for much of my career, I've worked in all aspects of network engineering. In the last few years, my focus has been on helping businesses around the world learn, design, and deploy network automation, some of which meant exciting close collaboration with my friends over at Network to Code. So we're going to walk through the four main categories in the center of this diagram, taking a quick look at some of the activities that take place and the tools and technologies available in each space today. The most common starting point in any automation journey is that of building a collection of tools, scripts, and platforms, which fall under the collective umbrella of the automation engine. This is the code that does the hard work, connecting to devices, applying configuration, running commands, fetching and manipulating data, generating reports, making or restoring backups. Let's begin by talking about configuration management for a bit. Traditionally, devices are configured through their CLI by a network engineer who applies a set of commands they prepared ahead of time or derived on the spot based on the current state of the device and the change request. In order to perform the same operation in an automated fashion, a script requires very clear instructions and accurate data. There is no human intuition or decades of experience that may fix issues on the fly as a person would when sat at the CLI introducing commands that don't work, or perhaps have unintended consequences. By using variable data and templates, configuration management tools like Ansible, Salt, or the underlying Python code leveraging the Jinja 2 templating engine can build a text representation of the vendor-specific configuration commands that need to be applied to the device. As a side note, you may also generate JSON or XML structured data if applying configuration through an API rather than the more familiar CLI. This variable data is very context-specific and it's structured, meaning it's organized and stored in a format that enables efficient access and modification. It may contain things like interfaces and their IPs, descriptions, and ACLs when dealing with a single device, but just as well it could define NTP and syslog servers which are shared across the whole data center. Where do you store it? Well, it could be YAML files tracked in a Git repository or data inside of a source of truth like Netbox. Templates are what ties the actual data to a specific device's operating system, configuration syntax. You may and should try to store your data in vendor-independent structures so that swapping a 48-port Arista switch for a Juniper one would require a change in the configuration templates, but not in the data model itself. Now that a piece of configuration has been generated, what can you do with it? Many of the tools also support applying the configuration to a device, which requires code that knows how to connect to a particular OS's CLI or API. But that's not all. With Ansible, for example, you can take the configuration and compare it to what's running on the device, reporting on differences. If you decide to apply it, you can also have Ansible create a backup first. Should you have new devices in need of provisioning or simply restoration after a hardware failure, configuration generation plays a central role in what's called ZTP or zero-touch provisioning. When bringing up a device from factory defaults, an automatic ZTP process can take care of finding out the correct configuration based on a unique identifier like the serial number or chassis MAC address. This identifier is what allows the provisioning system to fetch the relevant device configuration data from the source of truth. In the course of daily operations, to increase the reliability of the network as a whole, you will need to perform various compliance checks. Are all devices running their expected configuration? Are there any unsafe modifications left over from incident resolutions? It may take a person days to answer these questions manually for a relatively modest number of devices, instead of using an automated compliance checker, a fancy term for an Ansible playbook or a Python script, that could do the same validation much faster and much more reliably. Because let's face it, it doesn't get tired, it doesn't skip some devices because nobody will notice. To check configuration compliance, one may simply compare render text configuration files, one freshly generated, one from the device itself, or in more advanced setups, structured data directly, such as JSON formats of the configuration or the underlying YAG models. When dealing with legacy devices that do not have anything but the pure text-driven configurations, various tools exist to help parse and compare data. For example, Batfish, Cisco PyATS Genie, or TextFSM with NTC templates. Compliance goes beyond just configuration, but this is one of the easiest wins that provide a lot of value and can be iteratively expanded in time to cover more tests. But most importantly, it is an operation which is very cheap to run on a regular basis, at a minimum daily, and triggered on other events such as change windows and incidents. Speaking of changes, they always run the risk of some unintended effects, be it due to typos, invalid data, human error, or software bugs. This is where being able to, at a minimum, perform pre- and post-change validation becomes critically important. To start with, capturing command outputs before and after performing a change may be enough for a cursory glance by a human operator to decide that all is well, augmented by green lights in the network monitoring system. But more complex changes or simple ones made across tens or hundreds of devices cannot be reasonably validated manually. So you must be able to parse data into structured formats and compare the before and after through a script or a dedicated tool. I need to emphasize here structured data, since I'm sure many of you have had to compare the output of show IP route for large routing tables with ever-changing timers and spacing that makes side-by-side text comparison practically impossible. Now, not all validation has to be done at the time of the change window. There are some tools out there that perform offline testing of configuration changes, meaning that the tool does not connect to the device for its analysis. One such tool is Batfish, open source at its core with a commercial offering for advanced features that models configuration and state data into its own internal structures. You can then ask it various questions about the data model, for example, to find out the effects of an ACL modification or how routing tables will look after that OSPF configuration change. The software development world has been using automated testing tools for their code for decades already, and as such, a lot of experience and tooling from that space is mature and available for us to use. It's not only about code, the scripts, the Ansible playbooks, but also about the testing of device configurations and data that's fed into them. Even more recently, the continuous integration, continuous delivery, CI/CD, in short, the CI/CD practices becoming central to the DevOps philosophy have started to extend into related disciplines. I'm sure that you've probably heard by now the term NetDevOps being used here and there. Continuous integration states that each iterative change to a piece of code should be subject to a predefined set of tests that validate adherence to coding standards and perform other offline checks in what's called a pipeline. For example, in network automation, you might test that a repository of Jinja 2 templates still renders valid configuration output. The syntax is correct. After a change is submitted. A repository containing Ansible playbooks could be checked first for valid YAML syntax, a generic test, but also then parsed with a tool called Ansible lint for specific Ansible-related logic, such as the correct usage of modules. The CD part in CI/CD refers to continuous delivery, extended the automated pipelines to also deliver the new releases all the way to production. For networks, that might mean that a configuration template change that passes all the predefined tests in the CI stage will be considered safe enough to use in a staging or production environment, and therefore automatically deployed to the relevant devices. While the CI part is all about quick testing and building confidence in a baseline validity of changes and a lot easier to get started with. The delivery process will take a lot of gradual development and building of trust in order to make it safely all the way into production. Source of truth. We've talked about necessary structured data when building and parsing configurations, but where does it all come from? The role of a source of truth is to capture intended or desired state of the infrastructure. In order to build trust and ensure it's actually used, we must ensure that data is accurate, it's reliable, and make it easy to access or consume programmatically. Traditional network infrastructures have acted as the source of truth for decades, both the intent and the operational result all in one place. But that one place is actually distributed across hundreds or thousands of devices from multiple generations and vendors, and likely under the management of different teams. There is no documentation. There is documentation, someone is bound to say. Yes, at one point in time, you actually had documentation that was both accurate and easy to find. Due to the iterative nature of the infrastructure lifecycle, documentation is quick to become outdated and fragmented. While humans can do their immediate jobs by using a mixture of experience, tribal knowledge, and 2 a.m., Sev1, the world's on fire, adrenaline-fueled network discovery, and hopping between devices, machines cannot do this. Any sort of automation system you may build requires accurate and reliable data to do its work. The source of truth is actually a collection, or a gateway, not a single system. It's an aggregation layer for all the systems and databases that act as the authority for a particular type of data, also called system of record. For example, IPs will be in one database, servers and cabling in another, DNS somewhere else. Each of these should have exactly one system of record that uses the right data store for that particular information. In an ideal world, all of these would have an API, versioning, and audit trails. Unless starting from scratch in a greenfield situation, it's very likely that some of them, spreadsheets, will not be immediately and easily consumable in an automated fashion. Data stored for human consumption, it's formatted, good looks, is very often quite different to what a machine needs, structured data like JSON or YAML. So in the meantime, there will be some data duplication between systems as new ways of consuming it become necessary and adaptation layers need to be implemented in front of them. For example, you might bring in Netbox for data center management and populate its IPAM or IP address management module, but the system of record remains that info blocks that has been in use for years and is deeply embedded in many processes. Over time, you will naturally want to reduce data duplication to improve accuracy and reliability, but it has allowed you to make progress and achieve short-term wins. In building the components of your infrastructure's source of truth, a set of questions will repeat quite often. What information do I need to store? What format should it be in? Or how do I organize it? And how do I populate and keep it up to date? If starting from a brownfield environment, you will already have various fragmented information stores, with the actual running configuration on your devices very likely being central to it all. If you decide to use a centralized database for some of this data, one of the first steps is importing data from the current system of record, the network, into the future system of record, say Netbox. While this project is ongoing, you are in a data duplication scenario where the old system of record is not frozen in time. Other teams will be making changes and carrying on with their projects and daily operations. So the longer the transition takes, the harder the battle of keeping data in sync between the two platforms becomes. The end goal is to ultimately swap to the new system of record as having authority and change the direction of workflows. So instead of network towards database, have the database tell the network how it should look like. For greenfield environments, you can start by populating your chosen source of truth with data and keep using it as the gateway for any subsequent modifications. None of let's just quickly deploy it and we'll worry about documentation later. No. Okay, Cristian, okay, but what actual data should I be storing in this fancy new source of truth? Well, to start with, the most basic yet unmissable piece of data about your network. What's in it? You've got to have a device inventory to be able to target individual routers and switches, groups based on location, model, OS, version, role, and status. You may already be using your NMS as an unofficial inventory based on the handover to operations, or maybe have a change management database that also tracks device characteristics. It could be all you need if you trust that system to act as the inventory system of record, and the information can be guaranteed to be accurate and consumable via an API by other systems, which is pretty much where traditional or off-the-shelf legacy products fail to deliver. More often than not, once a system of record for the inventory is set up, you will be automating the synchronization of devices, onboarding, decommissioning into the monitoring tools, CMDB, ticketing system, etc. From there on, continue building the rest of the information you need about a device in order to generate its configuration from a template. Some of it might be the same across the whole network, NTP, syslog, DNS, SNMP, but a good amount will be device-specific data, interface-related configuration, routing protocol, switching, ACLs, and other policy constructs. As long as you have a reliable and accurate way of retrieving this data for a specific device, that doesn't include digging through 5 SharePoints, asking people that retired and writing a letter to Santa, the rest of the steps towards ending up with a correct configuration appropriate for the device's OS are fairly straightforward. Good data is key. In terms of solutions and products out there, you can already tell by now that there's no universal answer, the one source of truth to rule them all. You will need systems of record for IP address management, DNS and DHCP, device inventories, lifecycle management, configuration templating, data center infrastructure management, etc. And thus you will combine open source solutions like Netbox or NSOT with commercial ones like Infoblocks, version control YAML files, and spreadsheets, although hopefully less of the latter part, and even homegrown databases where nothing else fits your needs. Monitoring and telemetry. Today, our intention is to take a quick look at the new capabilities modern tools and workflows bring to the table, especially in the context of how they fit into the greater picture of the automation architecture. Infrastructure monitoring is not new. It's been around for decades with a variety of commercial and open source products that aggregate logs, gather metrics, draw graphs, and generate alerts. While the term telemetry has grown in popularity quite recently, it is part of a new wave of modern tooling that represents significant advancements in data collection, storage, and consumption. Traditional monitoring tends to be device-centric, with simple, event-driven alerts, common operational metrics, and limited historical data. A lot of the products are intended for human operators and, as such, have limited APIs and integration capabilities with other automation systems. This also has another detrimental effect in that it is near impossible to use the data, usually stored in a tool-specific database, for anything else outside of the features implemented into the tool itself. Modern tooling will immediately stand out in how it is organized. Rather than centralized and isolated functionality, the new telemetry and analytics technology stacks are split functionally into units that can be used for multiple purposes and also scaled independently: data collectors, data processing, storage, database, visualization, and alerting. For example, the ELK stack is a set of tools designed to work together, but ultimately independent of each other. E for Elasticsearch, RESTful JSON-based search engine and document-oriented database. L for Logstash, a data processing pipeline. And K for Kibana, a flexible visualization tool. The key takeaway is that these stacks are made up of disaggregated components which offer open interfaces for interoperation with other systems, making it possible to pick and choose products based on specific needs. One might shake up the tick stack, keeping Telegraph, the collector, and InfluxDB, but using Grafana for visualization, or even replace the data store with Prometheus. You get the idea. There's a certain amount of freedom to mix and match based on requirements that until a few years ago was simply not there. Mandatory caveat: it takes time and effort, like all things when you're customizing. Collecting data in the context of network infrastructure typically refers to receiving, also known as streaming telemetry, or pulling information as needed from devices, starting with the painful yet traditional screen scraping via the SSH CLI to SNMP, syslog, and netconf/resconf APIs. Getting data might be easy enough, but parsing and preparing it for storage inside of a database usually requires a fair bit of effort, especially in the case of freeform text, the mother of all last resorts, when structured data is not available. Where things become even more interesting is when you start adding additional metadata before sending it on its way, so-called data enrichment process. for example, by querying your source of truth for device role type location. You may think that this additional metadata is available anyway in your source of truth, so why duplicate it into the monitoring systems database? Well, enriched data makes for more powerful workflows and queries, leading to easier correlations when something non-obvious has happened. Consider you might be looking to graph a specific counter from 10 gig interfaces, so the operational speed, on leaf switches, the role, in the EMEA region, the location, or logs from all spines in APAC DC5, or prefix statistics for BGP neighbors to a specific ISP based on the circuit type across all sites. Orchestration. The final piece of the puzzle in today's overview is the orchestration system. When you get to this step, it's usually when you have already solved a lot of the other difficult challenges. You have automated a lot of individual tasks, the source of truth is fully used, you've got good monitoring and analytics, plus you've developed your culture and processes to trust these tools. I hope you celebrated properly, because getting to this stage wasn't easy and took a lot of hard work. At this stage, some of those individual tasks that were automated might already be coalescing into what we're going to call workflows. That is a series of tasks that split a complex operation into smaller chunks which can be executed in an automated fashion. For example, let's say you need to perform maintenance on a circuit. Seems like a simple enough task until you actually put all the tasks on paper that the system's affected. You need a ticket to track the operation, a list of contacts to notify, then actually sending the notifications. Is it Slack? Is it email? Is it both? Waiting for the allocated maintenance window, perform pre-checks, set the circuit as under maintenance, drain the traffic, perform other verification, confirm no impact, wait for actual physical maintenance to complete, test the circuit, restore traffic, perform post-checks, remove maintenance flags, send notifications, and update the ticket. This self-documented task list becomes the workflow which the orchestration system now has to perform and coordinate. The workflow engine, therefore, needs to be able to talk to a bunch of systems, several automation engines, ticketing, monitoring, corporate chat, email gateways, through some sort of machine-to-machine functionality, like API calls, webhooks, or remote procedure calls. It's where all that prior hard work actually comes in. Without systems that facilitate this sort of human-free interaction, you would not be able to implement such workflows. To begin with, it's not uncommon to leverage advanced functionality in existing tools and have partial workflows implemented in, say, Ansible Tower or your CI/CD of choice like Jenkins. They may not be orchestration platforms outright, but what they offer within their functional scope may actually be sufficient. Eventually, as requirements grow, building and maintaining, heavy emphasis on maintaining, your own custom system might be one solution, as is investigating other off-the-shelf products on the market. For example, Itential is a commercial workflow orchestrator promoting a low-code drag-and-drop graphical interface to build a service catalog of operations. Other commercial products in this space exist under the umbrella of terms like closed-loop network automation and intent-based networking, such as Apstro's AOS, Anudo's Atom, and Blueware. As a middle ground between building and buying, you will find full-feature open-source products like Stackstorm, where you have the ability to develop and customize yourself. But you can also leverage a third-party vendor support offering to help you along the way. So the orchestration system now has the capability of defining and executing various workflows. What's left is adding one last link to the telemetry or monitoring systems so that changes in operational conditions can trigger automated actions, as simple as gathering troubleshooting data or more advanced like performing automated remedial actions. This is what's also known as event-driven automation. Taking baby steps and building operational experience and ultimately trust is what's key here. Anyone can write scripts that shut down flapping interfaces, but ensuring that the code is well tested and safely executed is the hard part. Like, say, avoiding shutting down the same interface across all switches in the PODO region instead. In the end, mistakes will happen, and if you got to this point, most likely they have already happened, and you learn from them, improving your scripts and the workflows they're used in. Even the biggest automated networks in the world still make the news every now and then, with a global outage caused by a script removing more prefixes than it should from BGP advertisements, or my recent favorite, a simple CPU wrecking regex. The 2 days of the Network Automation Summit are packed full of introductory and advanced sessions covering many of the tools I've mentioned, be it Ansible, NetMiko, Napalm, Nornir, CI/CD, flows, Netbox, testing, PyATS, Badfish, and some fantastic stories and panel discussions. That's it from me for now. Do get in touch during the live Q&A, also later online. Thanks for watching, and until next time.